Hello, welcome to this video. So in this video we're going to be exploring something called chaos physics, which is the study of systems whose future state is very dependent upon the exact details of their initial state. So if we alter, say, where a particle is in a system, the system will behave very differently long term based on that tiny initial change. Applications are seen in climate change, they're seen in astrophysics, they're seen all over but in biology. And if you're a climatologist, you're probably familiar with the legend that if a butterfly flaps its wings in one place on the Earth, it might end up resulting in a tornado somewhere else due to how dependent the future state of the weather is on very tiny details of the weather's initial conditions, including the air currents around the butterfly. The idea of chaos physics kicked off in astrophysics, where somebody was looking at the future of the solar system and trying to work out, whether the planets will keep having the same kind of orbits, in the same order of planets in the long term that they do currently. Because it's often assumed by the way that planetary motion is modeled in high school that the only thing that really matters to a planet's motion is the sun at the centre of the solar system and the gravitational interaction between the planet and the sun. But there are tiny impacts by other planets as well. And so somebody was trying to take into account how a planet's orbit might be affected in the very, very long distant future. And he was writing a document, got to the end, had it published, and then after it was published he realised there was a tiny mistake, where he had given one of the values of one of the planets in the solar system's current position slightly wrong. It was very, very nearly right, but slightly wrong. But he was initially like, well, it doesn't matter. It's only a tiny, tiny difference to the true value. Won't really affect the final result. However, to be sure, he went through his calculations all again, but now with the correct value for the position of the planet. And I admire his work ethic, because at this time there weren't computers, so he had to do it all by hand, including all the computation. This shows how that chaos physics goes. And he realised that the planet would end up having a very different final motion, even due to that tiny change. Therefore, that planet's motion was, as we would say now, chaotic. So chaos physics has ran problems with the physicists. It's made sure we have to be very careful of our exact, or at least as close as we can do to exact values. It also means that experimental uncertainty might not be insignificant in some cases, and being unsure about the exact position of the planets, even when we know them very precisely, might mean a lot of our models for what will happen to the solar system might be something that needs to be called into question. So chaos physics has far-reaching implications for really actually all areas of science concerned with systems which are very sensitive to initial conditions. In this video, we're going to talk briefly about Hamilton's equations and phase space before looking at non-chaotic systems and then going on to chaos physics. I'm only going briefly through Hamilton's equations and phase space, which allow us to understand chaotic systems, because I've done a full video on Hamiltonian physics, which I put on the quantum field theory playlist, because Hamiltonian physics helps us understand how we can quantize quantum fields and get particles. Also, it helps us understand how quantum fields evolve and change, thus allowing us to talk about particle interactions. But in terms of classical physics, a beautiful application is chaos physics, which I didn't go into much detail in that video, so I'll talk about this now. So this will be a brief overview of Hamiltonian physics, moving on to non-chaotic systems, then chaotic systems, and we'll finish finally with talking about the three-body problem in astrophysics, and also one that has inspired science fiction novels. So, as mentioned, I'm going to briefly review Hamiltonian physics and the Hamiltonian. I really presume you've at least heard of it before. You don't have to remember it fully, but I'm going to presume it's fairly familiar. But if it isn't, give this kind of bit of a video a go. And if some more clarity is needed, there's a video on my channel, and there's videos on lots of other channels going through Hamiltonian physics in more depth. So Hamiltonian physics really concerns looking at how a system evolves based on how a quantity called the Hamiltonian varies. And the Hamiltonian represents the total energy of a system, so the sum of kinetic and potential energy of all the particles that make up the system. Although for many of what we'll look at here, there's only really the motion of one particle we're interested in, at least until we talk about three-body problem at the end of this video. But Hamilton's equations talk about the dependency of the Hamiltonian, so the total energy, on the position of the particle, so where it is in space, often in reference to something that is producing a field which is generating some force, and also on the kind of momentum of our test particle. Now, because we can represent position in many different ways with Cartesian coordinates or angular coordinates, we don't really want equations, if we can at all help it, that make reference to a particular coordinate system. So we just talk about generalised position in space. And there's associated with that the idea of a generalised momentum or conjugate momentum. Hamilton's equations are about how conjugate momentum and generalised position relate to each other through the Hamiltonian. So the first of our two differential equations, which together form Hamilton's equations, tells us that the partial derivative of the Hamiltonian with respect to conjugate momentum is equal to the time derivative of generalised position. Now that dot just means time derivative, and here we're using p to refer to conjugate momentum, q to refer to generalised position, and sometimes I'll put an I, particularly this is useful if we have many particles. So pi means the conjugate momentum, or in other words generalised momentum, of the ith particle. But sometimes we drop that, like if there's only one particle whose motion we're interested in, we often just drop the I because there's only one particle. It's very useful if you're considering multiple particles interacting with each other, which in technical jargon we say if you're dealing with a many-body problem. And then the second of Hamilton's equations is this one, and this one is a lot more useful usually. The reason is, whilst the top equation often reduces down, as we'll see when we look at a free particle, to saying that for any set of position coordinates, a good definition of the momentum is that the momentum equals the mass of the particle times its time derivative of generalised position. So in other words, a good definition of momentum generally is mass times velocity. The second equation it doesn't reduce to the same kind of statement for all classical systems. The second statement is much more about the forces or the potential energy of the particle. So the forces the particle is experiencing, or the potential energy of the particle, and therefore is a lot more significant usually because it varies based on the system we're dealing with. Whilst the first equation reduces to the same thing, as long as we're considering, classical particles, so they're not moving at relativistic speeds. And And when you put these two equations together, you can work out how Q and P vary with each other, and we plot that in something called phase space. So in phase space, we consider the position of a particle and its momentum, and if you look at how that will change over time, you'll kind of trace out a trajectory in phase space, and that trajectory will tell you how the position and momentum change, or in other words, how the state of your particle will change over time. And it's this kind of visualization that is really good, particularly for chaotic systems. But we'll come on to more of that later, and we'll see examples of real-world phase space diagrams for both non-chaotic and chaotic systems. But here we see that we have, well, here I've just plotted a particular trajectory in phase space, and this is something that we'll see in not too long for a particular type of system. But even without knowing any physics of that system, by just looking at the motion in phase space, you can immediately guess something about the behaviour of the particle in this system, because this circle is kind of a closed curve. And so what that tells you is if a particle starts in a state which it lies anywhere along this curve, it will end up going back to that same state. So you might think, well, this is referring to, say, a particle oscillating, or maybe even the orbit of a particle around orbit of a planet around a star. And we'll be talking about how this reflects kind of particles oscillating in a bit. And for those of you who ever looked at circular motion in great detail, you'll know that there's a very strong link between circular motion, or in other words, kind of orbital motion, and also oscillation. I won't be going into that here, but there is a reason why the two are connected and have a similar look similar in terms of phase space in at least some respects. So now we've had a very brief, I know it was brief overview of Hamilton's equations of phase space. Let's get going with some specific examples. So we'll start with a free particle, but then we'll build up to much more complicated things in this video before moving on to chaos. So we're now going to talk about specific examples of motions in phase space. So for a free particle, we essentially have a situation where the Hamiltonian is very simple, because the Hamiltonian is the total energy in the system, so the sum of kinetic and potential energy, but for a free particle it's not experiencing any forces, so the potential energy is zero, and therefore the Hamiltonian is just equal to the kinetic energy. So the Hamiltonian is momentum squared divided by twice the mass. Now we write the Hamiltonian in terms of momentum rather than velocity in Hamiltonian physics, because to get the equations of motion, we want to differentiate h with respect to either conjugate momentum, so that's p, or generalised position q. So we want to write h in terms of p and q. We don't want to write h in terms of q dot if we can at all help it. So that's why we write the kinetic energy as p squared over 2m rather than bringing in the idea of velocity directly into the Hamiltonian. Now the second of our equations on the last slide, the kind of interesting equation, if you like, tells us that the rate of change of momentum for a particle that's free, so one that is experiencing any forces, is zero. So the particle has a constant momentum and never changes its momentum. And this means that the particle has to move at a constant velocity, so at the same speed and in the same direction, which is essentially Newton's first law. So we get Newton's first law out of Hamilton's equations. Also, although I'm not doing it here, you can show if we have a generic Hamiltonian where the kinetic energy has this form, and the potential is assumed to vary on q and q dot, then actually Hamilton's equations will generically reduce down to Newton's second law, essentially F equals ma, which is a generalisation of the first law, with the first law essentially being a free particle has constant momentum, although it's usually rephrased in terms of velocity. And as we said, the first equation on the previous slide is just the rate of change or position, so in other words the velocity is just momentum divided by mass. So it essentially justifies that we can define the momentum always as mass times velocity, but the good thing is, because these are generalised coordinates, it means whatever coordinates we're picking for position, there's always a good associated momentum, which is given by multiplying mass by velocity, or the rate of change of position in those coordinates. So for example, you know, a good angular momentum would be the rate at which the angle changes times the mass. So it is quite powerful in terms of how general this equation is, and it's not stuck with just Cartesian coordinates. And if we want to look at the phase space see how the state varies by looking at trajectories in phase space for a free particle, well, a free particle has constant momentum. So if we ignore the zero thing in a bit, which is a coding artifact I'll come on to, but we look at other regions in the graph, other values of momentum, bearing in mind momentum is on the y-axis and position is on the x-axis. We can see that if we look at a line, the line is horizontal, so is referring to the particle having constant momentum. And so we see wherever we put the particle, so whatever line we start at, the particle will continue having constant momentum. And will change its position. Now, around zero, you'll see that we don't quite get a constant straight line, and that's because the code wasn't very happy when I put in the rate of change of momentum 0 as an initial condition, because when coding they use numerical approximations, or the computer does at least, and 0 is problematic for many reasons. You know, dividing things by 0 is undefined, 0 factorial is undefined. We have one of the few operations involving 0 that isn't fully defined is raising something to the power of 0. But because 0 is problematic, to get the code to work at all, I had to essentially go, well, I would approximate the rate of change in momentum as being very, very small, so not quite telling the computer it's 0, but going, well, it's whatever the position is divided by, 1,000 or something. So it's really, 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 really tiny. And what that means is for significant values of momentum, the code acted just as if I put in, for practical purposes, rate of change in momentum 0. But for tiny values of momentum, those tiny values became comparable to what I gave it as the rate of change of momentum, and therefore around 0 we see the computer thinks that there should be some more complex kind of evolution of the system, or motion of the free particle, as represented in phase space. But it's worth saying, for a perfect code, we would have a straight horizontal line at p equals 0 as well. Now we're going to move on to something a bit more complicated, so a harmonic oscillator. Well, there's various harmonic oscillators. An example is a mass on a spring. So we can consider placing the mass on a table and having the spring attached to a wall. And imagine this table is frictionless, so the system will never lose any energy. And we connect the mass to the spring. Well, initially the mass is going to be kind of stationary, and the spring is at its natural length, the length it wants to be at. And we'll call this initial position of the mass q equals 0. Essentially, our spatial coordinate system that represents the position of the mass has its origin at this current location of the mass, where the mass isn't experiencing any forces. well, at least, no force is caused by the spring, because the spring is at its natural length, it's not stretched or squished. However, if I move the mass, let's say I stretch the spring and then I release the mass, well, the spring has tension in it, and it's going to want to contract back to its original length, so it's going to accelerate the mass towards it. So the mass is going to be accelerated towards the spring. Then the mass will get back to the point Q equals 0, which we call its equilibrium point. There it won't feel any forces, but it will carry on moving on at a constant velocity at that point, thanks to Newton's first law. Because at that point, at that moment, it's essentially a free particle, but then as it goes past that point, it now starts compressing the spring, and the spring doesn't like being compressed, so the spring now wants to stretch back out to its normal length, and so wants to push the mass away. And then the mass is kind of flung backwards, passes the equilibrium point, and then stretches the spring as it keeps going, and then this repeats itself. And this kind of example where we have a repeating motion caused by a force that is constantly trying to get something back to an equilibrium position, it is an example of what's called a simple harmonic oscillator. Another example would be a mass, on a wire if it's moving like a pendulum. And this is simple harmonic motion because we're ignoring kind of drag, so there's no damping involved, there's no losing of energy. The Hamiltonian in such a case is just the kinetic energy plus some kind of potential term referring to this restoring force. And on a spring, thanks to Hooke's law, this term would be some constant, which would tell us at least in part about the stiffness of the spring, times Q squared. And it's squared because the potential, or the size of the potential at least, needs to be symmetric, because all that really matters is how far the mass has moved from equilibrium. Whether the mass has caused the string to be stretched or squished, the only thing that matters is how much the spring is stretched or squished, or in other words, how far the mass has moved in terms of the force the mass experiences, well, the size of the force anyway. And therefore, the size of the potential needs to be the same for both Q, if we pick a particular value for Q, and minus Q. And, an example of a very symmetric potential is kind of Q squared. And our first equation on the previous slide reduces down to saying, as before, that generalised velocity is just momentum over mass. We've already talked about that. But for this system, we get a much more interesting rate of change in momentum than we had for a free particle. We get it equal to minus, that's a new constant, times Q. Well, we can group 2K as just a new constant. And this ends up resulting in this motion in phase space. Now we see it's kind of circular, so the particle wants to return back to its initial state, and the arrows show the direction in the trajectory the particle will naturally trace out, due to this potential if we look at its state in phase space. And we can also see that we get circles, and we essentially get circles, at least in part, because, as I say, the potential is very symmetric, and in fact the only effect of switching Q to minus Q is the kind of like direction the force on the mass will act in. And that's why for any circle, the top half will be symmetric to the bottom half. Or I should say, for any trajectory referring to this potential in phase space, the top half will be symmetric to the bottom half, which in part justifies why we have circular trajectories. Now, this is an example of where we have a force that is getting bigger as Q increases. We can imagine if we stretch the spring more, it will want to even more firmly, at least until we start breaking the bonds or pulling atoms apart in the spring, it will even more strongly want to pull the mass or push the mass, depending whether the spring is stretched or squished. So we would expect for our mass spring system, as Q increases, at least the size of Q increases, the force and therefore the size of potential will also increase. But now we're going to look at a case where as Q increases, the size of the force drops, and that's actually the case for both the electrostatic force, so forces relating to the electric field, and also the gravitational force. And we'll talk a little bit about the electrostatic force on the next slide. Mention a tiny bit about the gravitational force, then we'll leave most discussion of the gravitational force till where we talk about the three-body problem at the end of this video. So on the previous slide we mentioned that we're going to now move on to the idea of electrostatic attraction and repulsion. Now, one reason we're doing this is because it allows us to discuss cases where forces diminish as Q increases. Another example would be the gravitational force. But what makes the electrostatic force quite unique and actually different to the gravitational force is that the electrostatic force can cause particles to attract, it can also cause them to repel. Whereas the gravitational force is only attractive, and that's because kind of in the universe everything we've found seems to act as if it has positive mass, and therefore everything seems to generate a positive attractive gravitational pull. And so, you can still theoretically, and people have done, talk about what happens if you've got negative mass, and you can use relativity to discuss that. One suggestion for dark matter has included what would happen if we consider shells of both negative and positive mass. And so, there are possible, applications of negative mass in explaining potentially certain phenomena, and negative mass might exist in this universe. But as far as we've established experimentally, everything seems to have positive mass, and therefore, because you can only have positive mass, it seems, at least as far as we know, for certain, or as certain as one can be about anything, it means gravity, for all intents and purposes, at least for now, can only be positive. Can only be attractive. Whereas charge, which is responsible for generating an electric field, can be negative or positive, allowing for cases of attraction or repulsion. So if we consider, for example, a source particle that's really, really heavy and is generating an electric field because it's charged, and we've got another much lighter test particle, which is also charged. Because the test particle is much lighter, its acceleration is going to be much more significant than the source particle, and therefore we can consider the two particles together as a system where it's only really the test particle that is moving. And if the test particle has the same sign of charge, so say they're both positive as the source particle, then it will be repelled from the source particle. But if the source particle and the test particle have opposite charges, then the test particle will be attracted towards the source particle. And in this model, we consider the source particle being at position Q equals 0, always. And we take the positions of the test particle based on the fact that our source particle is at Q equals 0, or at the origin of our coordinate system. And it also is mathematically easier if you consider the source as emerging from a point that is the origin of a coordinate system rather than emerging somewhere else. So there are mathematical reasons for doing it as well. Well, if we consider the Hamiltonian for such a system, so the sum of kinetic and potential energies, well, the kinetic energy is the same as before. We're not worrying about relativity. We're assuming the electric field isn't that strong. If it was really, really strong, we would start to have to consider about the magnetic field produced as our task particle moves at relativistic speeds. But we're not worrying about that. We're assuming that the task particle is only accelerated to, at least compared to the speed of light, very small velocities. So our kinetic energy of our task particle remains the same as previous expressions for our kinetic energy. Our potential has a size of k over q, k over q, because this is this is essentially the form that the electrostatic propulsion would or attraction would take, and we'll see that as q gets very, very big, the potential becomes zero, because as our task particle gets very far away from our source, it barely feels any impact from the source at all. Now, something to note about the plus or minus is that's to do with cases where we can have attractive or repulsive forces. So I'm usually quite relaxed in my videos, as is most of physics. If a force is always attractive or always repulsive, if it's like that, we don't really bother about putting a plus or minus in front of our force or our potentials. Where it becomes significant is if a force can be attractive or repulsive. And then we start to use a convention, and it's only a convention, but we stick with it to make everything consistent. So for attractive forces, we say that the force is negative. For repulsive forces, the force is positive, so it's bigger than zero. And the force associated with electrostatic attraction or repulsion it's worth remembering in inverse square law, so it's some constant divided by another constant times q squared. Meaning when we differentiate the force, if our force was positive, we're going to get something that's negative, and if our force was negative, we're going to get something that's positive. And because the potential is minus, because the force is minus the derivative of the potential with respect to q, and as we said, it essentially means that a negative force, so a attractive force, so where our task and source particle have opposite charges, will correspondingly have a kind of like, well, because our force is negative, the differential of the potential with respect to q would have to be essentially positive, which would mean, because the potential has q on the bottom, the potential would have to be negative. So that's a bit kind of like circular, but it's because of this convention, and also the fact that for the electrostatic force q is on the bottom, it ends up meaning negative potentials are going to be associated with attraction. So where our particles have opposite charge and our task particle is attracted to our source, we're going to have minus k over q, whereas when the force is repulsive, we're going to have plus k over q. So, I went through that in a bit of detail, but it's worth talking about a bit because this convention can get a bit confusing. And we'll see that we do get different graphs for attraction and repulsion, and identify which is what when we talk about positive and negative values for the potential when we look at our phase space graphs in a moment. And what this equation ends up reducing down to is, when we use Hamilton's equations, is these two statements about Q dot and P dot. And now let's have a look at our plots in phase space. Well, firstly, we get the case where the potential is negative, so we have the potential being minus k over q. And in this case, we get the time derivative of momentum also being negative. And that results in this kind of tendency of our test particle wanting to go to q equals 0, so wanting to go to our source particle. And you can see if the particle gets very, very far away, the curves on the trajectory, the trajectory in phase space starts to become more and more flat and become more and more like a horizontal line, indicating our particle is acting more and more like a free particle, and it will in effect take longer and longer to kind of like return back to this source particle. Essentially our test particle becomes better and better approximated as a free particle, or a particle that's mostly free but experiencing only a very, very weak force. Now we're going to look at what happens if the potential is positive. Well, in that case, our rate change of momentum just picks up a positive sign, and we clearly get repulsion. As you can see here, where the particle really wants to get as far away from the source particle as possible, and the closer our test particle starts from our source particle, the greater its acceleration away from the source particle. It flees away and therefore changes momentum as quickly as it possibly can. And it goes a bit almost mad as we bring our test particle right at the source particle. So we take our test particle to approaching q equals 0, because then the repulsive force becomes essentially gigantic. And so the momentum changes really, really drastically, and so before it's had much chance to change its position at all, it will pick up a huge amount of momentum trying to push it away from the source particle. And therefore we get kind of our curves start to approximate a horizontal vertical line. So a vertical line is associated with infinite forces, if you like, and a horizontal line is associated with no forces at all. Just a neat way to think about graphs in phase space. So we've talked about non-chaotic systems so far. They're non-chaotic because, at least excluding infinite forces, which we can't really get in nature, you'll never actually have the test particle overlapping the source particle due to quantum mechanics and Pare's exclusion principle, if nothing else. Classically due to the fact that it would take an infinite amount of energy to put them on top of each other if they're repulsive anyway. We're getting very, very similar motions in phase space, no matter where the particle, let's say the mass on the spring or the test particle, begins at. Assuming we have the same potential. However, a chaotic system is one where we have a fixed kind of expression for our potential, but we do get places in our phase space which look very different to each other, indicating that the behaviour is very, very sensitive to initial conditions, not just in terms of ending up with different values, although you could kind of justify that as chaos, but where you really undeniably get chaos is where you get very different behaviour at some point in your phase space, and that's what we'll be looking at in the next part of this video, before we talk about the three-body problem at the very end. So, we've talked about non-chaotic systems, now we're going to talk about a chaotic system. Now the beauty of having something like Hamilton's equations is you can play around with them for arbitrary potentials to your heart's content. And providing we're valid in the assumptions that led to Hamilton's equations. For example, we're explicitly assuming to get to Hamilton's equations that we can write the time derivative of the Lagrangian in a particular form, which requires the potential to only be a function of q and q dot. It can't be a function of, say, q dot dot, so acceleration. So providing you stick with those assumptions, you can play around and see what hypothetical potentials would result in what pass through phase space. Well, if you do that for, say, a Hamiltonian of this form, well, here I've assumed that there's some cubic force, and the nice thing about a cubic force is a cubic force does have a slightly unusual shape, and that gave me hope I would see something quadratic, well, something not necessarily quadratic, but something complicated emerging from this. When I said quadratic, I was probably thinking, if you use Hamilton's equations, you'll find that the rate of change of momentum depends quadratically on q, and we also get our usual definition of q dot as momentum over mass. And indeed, if you then plot Hamilton's equations in phase space for this system, you'll see that there's a point in this phase space where suddenly the kind of trajectory starts looking very, very different. And it's that sudden difference, as well as the fact that, points become quite densely packed, and in places quite densely packed trajectories are kind of quite steep, and therefore relate to, large changes in momentum. So even if they're close together, perhaps those changes could be significant. Tells you that we're dealing with a chaotic system. The main thing is that we get a sudden change somewhere in our phase space, and here it's around there. So that was a very brief look at a kind of, if you like, toy model, as one calls it, a kind of made-up potential but showing a very real effect seen in physical systems that display chaos. Now we're going to talk a little bit about the three-body problem. Now, at some point I might properly do a video fully on going through a chaotic system in detail. However, that's the maths of chaotic systems does get quite complicated, so hopefully you'll forgive me if, having seen an example of a chaotic system and many ways to interpret phase space diagrams, we just talk a little bit about the three-body problem, and kind of leave our discussion of chaos physics and phase space, at least for the moment, there. So, mention we're going to move on to the three-body problem. A good place to, well, at least gravitational physics and the three-body problem. A good place to begin is really what the three-body problem is. The three-body problem, as a slight aside for any sci-fi fans, has got such notoriety that it's kind of inspired stories, quite a few stories by many authors. But there's one really wonderful series recently that has been made based around the three-body problem. written by a Chinese author whose name I will probably pronounce poorly. My pronunciation isn't great at the best of times, but I think it's Liu Sheng, if I'm pronouncing that right. If not, and you're familiar with the right pronunciation, I do apologise. But the series kind of focuses around, if you don't mind, a tiny bit of a spoiler, though I'll be very light and won't give anything too heavy away. Um, of kind of world inhabited by aliens, where this world has 3 suns. And due to the very complex motion of these suns, which whose physics is essentially described by the 3-body problem, these these stars mean that this planet enters periods where it's really, really great for life and where the civilization of this alien species can flourish, and other times where the civilization faces huge kind of catastrophic challenges, thanks to being different, very, very different, but the planet having a very different environment. Due to the chaotic kind of nature of this kind of 3-star motion. And the book series is wonderful because partly it's inspired by very real physics, and also it goes into great depth about human psychology surrounding the idea of aliens, and if the world was filled with alien species, how would the aliens think about each other? So it's psychologically, and also it has a lot of interesting statements to make about religion as well in it. So it's a really wonderful series I would recommend listening to, particularly if you're interested in hard sci-fi that's kind of quite philosophical or quite thought-provoking science fiction. So the 3-body problem has been around even in literature, but in physics, to be specific, the 3-body problem concerns the situation where you have 3 masses, let's say, for example, 3 stars, and all the masses have similar-ish masses to each other. By that I mean there isn't one, say, star which is much larger or much less massive than the others. And therefore, if we're considering this system freely, rather where the system as a whole is freely in space, then these stars are going to feel significant gravitational interaction, and the gravitational interaction will occur between all pairs of stars. So let's say we've got stars 1, 2, and 3. Star 1 will feel a gravitational force due to star 2, but it will also feel a gravitational force due to star 3. And so every star is feeling 2 distinct types of forces. And this makes the motion of all the stars really entangled, and therefore, unsurprisingly, leads to a chaotic system. And we could go through the at least mathematical underpinning of what makes the 3-body problem challenging here, but it does ultimately relate to this kind of entangled nature of the sets of equations concerning these 3 masses. So firstly, we will write down Hamilton's equations, the Hamiltonian, for our 3-body system. Now here are our subscripts which tell us what, say, star we're referring to. So I runs 3 values 1, 2, and 3, as does J. So like M1 would be the mass of star 1, M2 would be the mass of star 2, M3 would be the mass of star 3. And the gravitational force described by a potential term depends on the product of the masses of 2 stars. So it could be say mass 1 times mass 2, and although we haven't written it here, it's supposed that I and J can't be the same, because a star doesn't respond to the gravitational force it itself creates due to its own mass. That kind of thing where you have an object creating a force that it itself responds to is something you only really see in quantum mechanics. But this is classical physics, so it doesn't happen here. And we get Qij, which is the distance between mass the distance between mass I and mass J. Because obviously the further apart those two masses are, the weaker the gravitational force. And so we've talked here about our potential, and our kinetic energy is just the sum of the kinetic energy of all our masses. Hence we've got kind of the sum of I over pi squared divided by 2m. Now, what makes this equation really tricky to solve is, to start off with, we can clearly see that we're not writing the potential in terms of coordinates, like in terms of qi or qi dot. And the reason is because the motions of each mass are so entangled with the others, we can't actually define a point in space where the potential has a suitably characteristic value for us to meaningfully measure the masses, the distance for a particular mass, and talk about the potential in terms of that distance. Whereas, say, when we looked at Hooke's law, we were like, well, the spring generating the force, there's a potential associated with the tension in the spring when the mass starts moving, and the potential reaches infinity if the mass gets too far out. But if the mass is at its equilibrium position, so if Q is 0, then the potential is 0. So it made sense to describe the potential as essentially distances away from Q equals 0, where the potential itself equals 0. With the electrostatic force, it's almost the reverse. It's where the potential is infinite at Q equals 0, and the potential is 0 at Q equals infinity. But we still had very clearly defined points where we could meaningfully talk about the potential about in terms of a function of distances from that kind of origin. And whereas with our three-body problem, because the masses are so entangled in their movements, we can't define meaningfully any such stable, constant point where our potential is either infinite or 0, kind of consistently throughout time, meaning we can't meaningfully really consider the potential being a function of distance q from a particular point. Instead, no, the potential depends on multiple distances, with each distance being dependent upon the position of a pair of masses, with those pair of masses changing position, meaning that Qij is itself a dynamical variable that can change. And so it's due to the fact that we can't define the potential really in terms of Q or Q dot anymore. And the fact that it's dependent upon multiple values of Qij, all of which are dynamical variables, that means that we have very entangled movements of the masses, and so you might naturally think, well, if you change the position of one mass slightly, it will dramatically affect the final result, because the motions are so entangled. This tiny difference initially is going to lead to quite drastic differences very quickly. So that has been a fairly qualitative overview of the three-body problem, and it's worth saying there's a lot of progress to be done still on this problem. There's a slightly easier problem called the restricted three-body problem, where we consider, for example, 2 planets and an asteroid. Now, an asteroid has much less mass than the 2 planets, so in this situation what you can do is consider the motion of the masses separately to the asteroid, because the masses will barely be affected by the asteroid at all because they're so much heavier. And so our planets can be modelled in their motion as a two-body system that you can solve exactly using Hamilton's equations or Lagrangian mechanics. And you'll see that there's leads to elliptical orbits about a common centre of mass. And then you can bring in the asteroid, your third body, if you like, and see how it's going to react to the gravitational field generated by these two moving masses. And that leads neatly to the study of what are called essentially Lagrangian points, which is where the gravitational force from the two masses cancel out and the asteroid doesn't feel any net force. And Lagrangian points are important for planet development because at these points, for example, if something is trying to form there, and well, it won't be ripped apart by say the two planets. So if we're considering things forming in a planetary scale, then the Lagrangian points are very useful. So if you're interested in the history of the solar system and how it formed, then Lagrangian points and the restricted three-body problem is of a lot of interest there. But the three-body problem has a lot of work to be done in solving it, really understanding even the approximate solutions, and well, it's still very active in research and also very active within the minds of science fiction authors. So, this has been a fairly, well, I would say brief, it's a fairly long video, but a fairly light, I suppose, overview of chaos physics. If you would like to learn chaos physics in more detail, there are some really good books out there, such as one which covers chaos physics for physicists, chemists, and biologists. Because chaotic systems are seen over nature, but I hope this video has given you a feel for chaotic systems at least, and a detailed understanding of phase space. And if you like this video, then please check out my channel for more videos. On this channel we mainly focus on quantum physics and relativity, but we do bring in other things like classical physics, chemistry, and I'm hoping to do a bit more on biological physics at some point. So if you're a biologist, there'll hopefully be something for you on this channel soonish. So hope you've enjoyed it. Have a really good day, and hopefully see you for another video soon.